penicillin is a gift from God to humanity. And that miracle emerged as a fungal spore which fell upon Alexander Fleming's culture plate. And that fungal spore changed the history and destiny of mankind. The penicillin is a cornerstone of modern medicine. Alexander Fleming was a bacteriologist working in St. Mary's Hospital in London. In 1928, he was working with Staphylococcus aureus culture plates. He was going on vacation, and just before going on vacation, he heaped all his culture plates in one corner of the laboratory. And when he came back from the vacation, when he opened the plates, what he noticed was in some of the culture plates, the Staph aureus growth was eliminated by some fungal spores which fell on those plates. So what we observed was something from those fungal colonies is killing Staphylococcus aureus bacteria. So that should be a chemical material which can kill the bacteria. And that's how penicillin was discovered. That day, Alexander Fleming really didn't really understand the significance of what he has discovered. But later, the modern medicine realized how significant penicillin was and how significant antibiotics are. But nowadays, we are going to live in a world without antibiotics. Because we overused penicillin, we overused the rest of the antibiotics. More and more antibiotics were introduced into the armamentarium, and at one stage we believed that we have conquered the challenge of infections. We overused antibiotics, we underused antibiotics, and we misused antibiotics. Is penicillin the first antibiotic? Of course no. In 1909, the first antibiotic was discovered by Paul Ehrlich and team, and the name of that antibiotic was Salvarsan. Salvarsan was used to treat syphilis. Unfortunately, that first antibiotic was so toxic, the patients complained against Paul Ehrlich and team. They complained that the scientists have produced a chemical compound which is so toxic, and just to fleece money out of the patients. The drug was so toxic. In 1912, Ehrlich and team, they discovered a new molecule. They modified the Salvarsan called as Neosalvarsan, which was less toxic than the original Salvarsan molecule. Again at that time, it was used to treat syphilis. In 1920 is a landmark. The first sulfonamide was discovered. The name of the sulfonamide was Prondocil. Prondocil is the first sulfonamide discovered in the history. And 1928, we discussed that Alexander Fleming discovered the penicillin. And the name of that fungal spore was Penicillium notatum, a part of history. 1931, the penicillin soak cloth was used to treat eye and skin infection. It was discovered in 1928. Penicillin was discovered in 1928, but the extensive usage started in 1930s and later 1940s. In 1941, the penicillin was used for treating sepsis in a policeman who had a rose thorn injury. He developed Staphylococcus sepsis. Penicillin, a lot of penicillin was used. It was crude penicillin, but the patient died. In 1939, Domac was awarded Nobel Prize for the discovery of Prondocil, the first sulfonamide. So it was not Alexander Fleming who received the first Nobel Prize for antibiotic discovery. It was Domac, and Domac was a German bacteriologist. At that time, Germany was not in good relationship with the rest of the world. Domac could not even come out of Germany to receive the Nobel Prize. He was not allowed to receive the Nobel Prize. Later, after the Second World War, the Nobel Prize Committee held a special meeting just to give Nobel Prize to Domac. 1942, the first time septicemia was successfully cured by penicillin. 1942. And 1942, Russians discovered another antibiotic, gramicidin. You will all note that all these antibiotic developments and discoveries at that time happened during the Second World War. In the war, patients were dying, soldiers were dying. They needed a molecule to cure sepsis in soldiers. In 1943, the British Prime Minister Winston Churchill is saved by an antibiotic. He had a very severe pneumonia, and he received a sulfapyridine, which is another sulfonamide, and his life was saved by an antibiotic. And 1943, streptomycin was discovered. At that time it was used to treat tuberculosis. It's the first anti-tuberculosis agent. 1939 to 1945, we all know that's a time of the Second World War. Thousands of soldiers were saved with penicillin alone. And that's how the penicillin was purified, developed and marketed to treat soldiers. The Western Ally needed a molecule to save their soldiers, and that was penicillin. And the Russians had their gramicidine to save the Russian soldiers. 1945, the first oral penicillin was discovered. And 1945, Alexander Fleming received Nobel Prize for the discovery of penicillin, a landmark here in the history. 1947, chloramphenicol is discovered. 1949, erythromycin was discovered. 1948, the first tetracycline was discovered. And 1950, colistin was discovered. 1950, colistin was discovered. And still, one of the most common antibiotics in tertiary care centers is colistin. An antibiotic discovered in 1950 is now brought back to treat multi-drug resistant, extensively drug resistant infections. 1952, the discovery of vancomycin. This is the history of antibiotics till 1952. So how antibiotics created that miracle? How antibiotics kill bacteria? And this is the mechanism of action of antibiotic. Let's look at the cell wall of gram-positive and gram-negative bacteria. If you look at the gram-positive, you will see a big on the top, the peptidoglycan layer, a very thick peptidoglycan layer. And beneath that, we have the plasma membrane. But look at the gram-negative bacteria. In the middle, you will see a thin peptidoglycan layer. On the top, there is a outer cell membrane, which is a characteristic of gram-negative bacteria. And inside, like a gram-positive bacteria, we have the cell plasma membrane. Both gram-positive and gram-negative bacteria have the plasma membrane, but the gram-negative bacteria, in addition, has the outer cell membrane and a thin peptidoglycan, where gram-positive have got a thick peptidoglycan. It's a very important difference between gram-positive and gram-negative. I'm going to show another picture, but concentrating on the same idea. The gram-positive on this side, gram-negative on this side. Gram-negative, you will see that this is the outer cell membrane, and then there is a thin peptidoglycan layer, and there is a plasma membrane inside. On the other side, gram-positive have got a plasma membrane inside, and there is a thick peptidoglycan layer, and there is no outer cell membrane. Now this difference is important in the mechanism of action of antibiotics. This is how antibiotics act. Some of the antibiotics act on the cell wall and inhibit cell wall synthesis. Beta-lactam antibiotics like penicillins, cephalosporins, carbapenem, aztreonam, they all inhibit the cell wall synthesis. Glycopeptides like vancomycin, teicoplanin act on the cell wall, again inhibit the cell wall synthesis or change the structure of the cell wall, killing the bacteria. Look at the metronidazole on the side. Metronidazole inhibit the DNA synthesis. So metronidazole acts on the DNA and inhibit the DNA synthesis. Quinolones like ciprofloxacin again acts on the DNA gyrase enzyme and inhibits the DNA synthesis. Rifampicin on the other hand inhibits the RNA, it acts on the RNA polymerase enzyme, again inhibits the nucleic acid synthesis. Look at the protein antibiotic which inhibit the protein synthesis directly by acting on the ribosome. The bacterial ribosome have got two components, the 50S ribosome and the 30S ribosome. Some of the antibiotics act on the 50S component. Macrolides like erythromycin acts on the 50S component. Chloramphenicol acts on the 50S component. Clindamycin acts on the 50S component. On the other hand, we have antibiotics acting on the 30S component. Tetracyclines, streptomycin, spectinomycin, kanamycin. So tetracyclines act on the 30S component, aminoglycosides acts on the 30S component, inhibits the protein synthesis, killing the bacteria. And some of the antibiotic acts on the cell membrane. the cell membrane. Polymyxins acts on the cell membrane. Polymyxins acts as a detergent, destroying the cell membrane. When cell membrane is destroyed, the bacteria die. If the cell wall is destroyed, bacteria die. Protein synthesis is inhibited, bacteria die. DNA synthesis is inhibited, bacteria die. If the cell membrane is disrupted, bacteria die. So bacteria acts, different antibiotics acts on various sites of bacteria. They have got different mechanisms of action. Now, are bacteria just waiting there to be attacked by antibiotics? Just like any living creature. If somebody attack a living creature, that living creature always develops their own defense mechanisms. Bacteria develop their own defense mechanism. They try to inactivate the antibiotic. They try to defend the attack by antibiotics. And some of the bacteria are intrinsically resistant to certain antibiotics. Look at the example of penicillin. Penicillin is not active against gram-negative bacteria. You know that cephalosporins are not active against enterococci. This is called as intrinsic resistant. They are born with resistant, intrinsic resistant bacteria. And it's a big list. Example, as I mentioned, penicillin is not active against, crystalline penicillin is not active against gram-negative bacteria. Cephalosporins are not active against enterococcus. Meropenem is not active against MRSA. This resistance is not developed. They are intrinsically resistant. And then we have resistance. Bacteria develop resistance. This is called as acquired resistance. And there are mainly two mechanisms of acquired resistance. Bacteria develops mutations. Under pressure, under selection pressure, bacteria develop mutations. And then when the bacteria multiply, the mutant genes are passed to the generations and generations of bacteria. On the other hand, if a bacteria has got a resistant gene, that bacterium can pass over the genes to the neighboring bacterium. It's called as transferable resistance. The resistance from one bacteria, the gene can be transferred to another bacterium through various mechanisms. And the simplest one is called as conjugation. When bacteria come together, certain bacteria, they develop a tube, a connection tube between the two bacteria. And then the resistant element, especially those resistant genes situated in the plasmid part of the cell, is easily transferred to the next bacterium. It's called as conjugation, transfer of resistance mechanism through conjugation. Typical example of transferable resistance. So we have got acquired resistance, we have got mutational resistance, and we have got transferable resistance mechanism. And how bacteria attack the antibiotics? They attack the antibiotics in various ways. We have so many antibiotics killing the bacteria in so many ways. So bacteria have developed their own ways in activating the antibiotics or defending the enzymes, antibiotics in their own way. One example is called as decreased permeability. The antibiotic has to enter inside the cell. So what bacteria does is, bacteria close off the porine channels or the holes in the cell wall so that the antibiotic cannot enter the cell. It's called as decreased permeability. The antibiotics can't enter the bacterial cell. They are shut out. Decreased permeability. And then, antibiotic can enter inside the cell, but bacteria have got efflux pumps. Those antibiotic entering the inside the cell are actively pumped out of the cell to outside the bacterial area. It's called efflux mechanism. And then bacteria inactivates the antibiotics. Penicillin is destroyed by penicillinase enzyme. Cephalosporins are destroyed by cephalosporinase enzyme. Carbapenems are destroyed by carbapenemases. These are the typical examples of inactivation, enzymatic inactivation by bacteria. And then we have altered target sites. Just change the shape and the look and the structure of the target. Antibiotics acting on ribosome, you change the ribosomal target. So antibiotics can't get attached to the target. Penicillins attach to the penicillin binding protein. So what does MRSA do? MRSA, penicillins or beta-lactam antibiotic can't get attached to the penicillin binding protein. So antibiotics can't act. That's called altered target site. Quinolones, what bacteria does? They change the target in the DNA so that quinolones can't act. So, but bacteria have various mechanisms of defending each and every antibiotic. It's not always one mechanism. Many antibiotics, for example, carbapenem resistance, you have carbapenemase enzyme, you've got porin channel loss, you've got efflux pump mechanism. So, bacteria have developed their own multiple mechanisms to defend antibiotics. Inactivating enzyme, we discussed the inactivating enzyme, penicillinase, cephalosporinase, carbapenemase, and there is a group called as extended spectrum beta-lactamase. Extended spectrum beta-lactamase means bacteria produce ESBL enzyme, and that enzyme inactivate penicillins, inactivate cephalosporins, inactivate astriona. So these are extended spectrum beta-lactamase. Carbapenems are ESBLs can't act on carbapenem. So one of drug of choice against ESBL producing bacteria is carbapenem group of antibiotics. Or we can use BLBLI group, beta-lactam inhibitor combinations. They inhibit the extended spectrum beta-lactamase. So BLBLI groups are active against bacteria producing ESBL, carbapenems are active against bacteria producing ESBL. One problem with ESBL producers is that not only penicillins, not only cephalosporins, not only astriona, they may inactivate, they may have the genes making them resistant to aminoglycosides or quinolones or other antibiotics. The reason is the ESBL gene is situated in the plasmid part of the bacteria. The same plasmid can carry genes for quinolone resistance or cephalosporin resistance or other antibiotic resistance. That's why ESBL producing bacteria are resistant to a wide group of antibiotics. And ESBL producing bacteria is not a rare phenomenon. In India, in majority of the hospital, majority of the gram-negative bacteria like E. coli, Klebsiella are ESBL producers. In many hospitals, 70 to 80% of the Enterobacteriaceae group. Enterobacteriaceae group means bacteria living in the gut. Typical example, E. coli, Klebsiella, Proteus, Morganella, Serratia. It's a big group, Enterobacteriaceae group. And majority of the Enterobacteriaceae in Indian hospitals are ESBL producers. That means majority of the antibiotics are not active against ESBL producing bacteria. That means majority of the antibiotics are not active against Enterobacteriaceae in Indian hospitals. Then aminoglycosides. Aminoglycosides can be inactivated by aminoglycoside modifying enzyme. Chloramphenicol can be inactivated by chloramphenicol acetyltransferase. These are all inactivating enzymes produced by bacteria. Decreased permeability, we discussed that. The porin channels can be closed off so that the antibiotics can't enter inside the cell. And then the efflux pump, bacteria pump out the antibiotics. Carbapenems. We use a lot of carbapenem like imipenem, meropenem, ertapenem, doripenem. And bacteria have multiple mechanisms to defend the carbapenem antibiotic, act against the carbapenem antibiotics. One of the major mechanisms is by production of carbapenemases. And there are different types of carbapenemases. The beta-lactamase produced by the bacteria is a wide spectrum. And scientists have devised a classification for the beta-lactamase. The most famous or most commonly used classification is called as the Ambler classification. A-M-B-L-E-R, Ambler classification. You will come across this term quite often in your clinical practice or academic practice. The Ambler A, B, C, D. These are the various subdivisions of beta-lactamases. I will give you a typical example of class A beta-lactamase belonging to the carbapenemase. That is KPC. It belongs to a group called serine metallobeta-lactamases. Serine metallobeta-lactamase, typical example KPC. Klebsiella pneumoniae carbapenemase. And this is the commonest mechanism of carbapenem resistance in the Western world. If you look at a carbapenem resistant E. coli or Klebsiella in America or Greece or Turkey, the commonest mechanism is KPC, the Klebsiella pneumoniae carbapenemase. If you look at the carbapenem resistance mechanism for E. coli or Klebsiella in India or other South Asian countries, it's called as NDM, the New Delhi metallobeta-lactamase. So, The South Asia, the commonest carbapenem resistance mechanism for Enterobacteriaceae, E. coli and Klebsiella are NDM1, New Delhi metallobetal lactamase, while in the Western world it is KPC, Klebsiella pneumonia carbapenemases. So typical example of class A carbapenemase is KPC, and typical example of NDM1 for B, class B is NDM1. NDM belongs to the class B Ambler classification of carbapenemase. This is a very, very beautiful illustration of resistance mechanism by bacteria. This is, I got this picture from New England Journal of Medicine, an excellent illustration. On one way, on the top, you can see that antibiotics are entering the cell through porin channels and acting on various target sites. And if you block those porin channels, antibiotics can't enter the cell. And on this way, you can see efflux pumps. Antibiotics are pumped out by the bacteria by efflux pumps. And you can also see that bacteria is producing various mechanisms altering the target site, and bacteria are producing various enzymes to inactivate antibiotic. And there is a very good illustration of lipopolysaccharide of the cell membrane, and that's where the colistin acts. And if there is an alteration of that site, colistin become resistant. This is how antibiotics act on the bacteria, and this is how bacteria fight back to save themselves from the action of antibiotics. If you don't know the past, you don't know what the present is, and you don't know what the future is. We looked at the antibiotic history till 1952, and what happened after that? In 1957, various chemical modifications of penicillin became available, and penicillin was so commonly used at that time. And 1962, the metronidazole was discovered in 1962. 1969, the Swan report recommends restriction of use of antibiotics as growth promoters in animals. You may wonder why a medical doctor is talking about antibiotic usage in the veterinary practice. I will tell you one thing. If you use 1 ton of antibiotics in hospital practice for human usage in the world, many times, many tons of antibiotics are used in the veterinary practice. One recent data shows that 80% of the antibiotics used in the world are not used for treating infection in the human world. They are used in the animal practice. And friends, you know why antibiotics are used in animal practice? Yeah, to treat infections, to give as prophylaxis against infection, but that's only a small part of antibiotic usage in the veterinary practice. The majority, the big bulk of antibiotics are used in the veterinary practice not to treat infections, not to prophylax against infections, but as growth promoters. Antibiotics are given as growth promoters so that animals grow fast and fat. How can antibiotics make animals grow fat and fast? We all know that intestine, including humans or animal, is full of bacteria. A part of the food that we eat are eaten up by the bacteria. So how can you prevent this bacteria stealing our food? Kill the bacteria. Kill the bacteria so that whatever food eaten by us or animals are absorbed into the body so that we can grow fat and fast. So give animals antibiotic. You mix a lot of antibiotics in the animal feed and give it to animals so that the bacteria in the animal gut die. So all the food is absorbed into the body of the animals. So animals grow fast and become very big. So that a lot of meat is produced. You can get a lot of profit. What's the problem, but why can't we do that in humans? If all the in the gut bacteria die, we can't live long, because bacteria are essential for the human life. If you look at the number of the bacteria in the human body, if you just count the number of bacteria in human intestine, that is many times more than the number of cells in the human body. The human body contains more bacteria than human cells. We are more of bacteria than human beings. We can't kill the bacteria in the human gut. We can't live without bacteria. Animals, yeah, they are going to be killed anyway. They are going to be slaughtered. So it doesn't matter, a good part of their gut bacteria are killed. They are going to be killed. The moment they grow fat, they are butchered. A lot of antibiotics in the world are used in animal practice. Is it something good? Of course no. If you give antibiotics to humans, bacteria become resistant. We develop multi-drug resistant bacteria. If you give antibiotics to the animals, same thing happens. You may know that even colistin is used as a growth promoter in the animal world. If you give antibiotics in the animal practice, animal farms, animals develop resistant bacteria, and then we humans get resistant bacteria from animals. One of the main reasons for antibiotic resistance in the world, including the human world, is the development of usage of antibiotics in the animal world for growth promoter and then passage of that bacteria into the human world. Swan report in 1969 is the first major report on the problem of antibiotics in the veterinary practice as growth promoter. The Swan report in the UK published the report explaining the danger of antibiotic usage in the animal practice as growth promoter. 1976, a very, very important milestone in the history of antibiotics. The first carbapenem was discovered in 1976. One of the most important carbapenem used today is developed in 1976. Years and years ago, that antibiotic was discovered. 1976. 1985, Sweden is the first country in the world who produced a law to regulate usage of antibiotics in veterinary practice as a growth promoter. 1985. It was followed by 1994. Denmark banned the usage of antibiotics as growth promoter in animals. It's a very landmark step, especially the ban in Sweden and later Denmark. There are very important landmarks of antibiotic regulation in the world. 1997, the World Health Organization started appreciating the significance of or appreciating the danger of antibiotic usage in the veterinary practice, and WHO called in a meeting of all the countries to discuss the danger of antibiotic usage in the veterinary practice. 1997. And 2001, linezolid was introduced into the market in 2001. And 2006, that means many years after the Swan report and many years after the WHO meeting, in 2006, European Union bans antibiotics as growth promoters in the veterinary world. 2012, you will know that for the last few years, the whole world is discussing about antibiotic resistance. Global leaders are discussing about antibiotic resistance. American president is discussing, the British Prime Minister is discussing, leaders of many countries are discussing on antibiotic resistance. Nowadays, if you attend an antibiotic resistance meeting, most of these high-level meetings are attended by politicians and policy makers, not just doctors, not just scientists, politicians and policy makers, because politicians control the policy and policy makers make policy. We can't control antibiotic resistance unless we have involvement of politicians and policy makers. In 2012, friends, there are two major initiatives called GAIN and FDASA. These are initiatives for stimulating antibiotic discovery. And 2013, now I am quoting all these milestones, antibiotic history milestones, are from a recent report by UK Antibiotic Action. UK Antibiotic Action is one of the most prestigious initiatives to tackle antibiotic resistance in the world. And UK Antibiotic Action team recently published a brief history of antibiotics. They included all these very important milestones. And 2013, according to the UK Antibiotic Action brief history of antibiotics in the world, they included a very important milestone from India that's called as Chennai Declaration. The Chennai Declaration was very instrumental in bringing out a modified rule to rationalize over-the-counter sale of antibiotic in India. And this is the only one mention in the history of antibiotics anywhere from Asian countries. And this is actually the only initiative by non-government organization ever got an entry into the history of antibiotics, in the world history of antibiotics. This is a very important achievement for India and Indian medical societies, because Chennai Declaration is an initiative by Indian medical societies with the help of Indian government. 2014, the World Health Organization published its first report on the global status of antibiotic resistance. First report by World Health Organization on the global status of antibiotic resistance. And 2015, a new class of antibiotics was discovered called as Teixobactin. It's the first new class of antibiotic after 1988. It's still in the very early stage of development, but it has got entirely new mechanism of action. This antibiotic is not going to solve the antibiotic resistance crisis because Teixobactin is active against gram-positive bacteria. It may take up to 10 years to be developed. The problem with NDM1 producing bacteria or KPC producing active bacteria, we have only 2 or 3 antibiotics active against this bacteria. One is colistin, one is tigecycline, and sometimes aminoglycans are active, and sometimes 1 or 2 other antibiotics are active. Colistin is the only reliable antibiotic against NDM1 or KPC producing gram-negative bacteria in the world. And we are all facing a scenario where we are too much dependent on colistin. And colistin resistant isolate has started appearing in many countries including India. And we don't have antibiotics to treat colistin resistant bacteria. This is what is called as the post-antibiotic era, otherwise called as the pre-Alexander Fleming era. At the height of the 21st century, with all the development in the technology, development in the science and development in the world, we are talking about a modern medicine without antibiotics. And who created this scenario? Human beings. Medical community created it. Patients created it because patients are also, patient pressure is an important factor for antibiotic prescription by doctors. Antibiotic resistance scenario, such a very important or dangerous scenario was created by humans. Antibiotic resistance affects all. No antibiotics, no cure. And antibiotic resistance is one of the 3 greatest threats to human health. One of the 3 greatest threats to human health. This is by the World Health Organization. Thank you.